Hello, General Biology, and welcome to Chapter 2. We're going to do the first in the screencast series for Chapter 2. This is Section 2.1. And Chapter 2 takes a look at the molecular part of biology. So we have to learn a little bit of chemistry in order to be able to understand reactions and cycles and processes that we're going to be talking about when we get there later on in the year. So I will have to say that for those of you that had Mrs. Mitchell last year, this is going to be somewhat of a review, so that's going to be good for you. And those that did not, this is going to hopefully be a little bit of review of what you learned in science before, but taken a step further. I will tell you too that your understanding of this chapter is going to be vital to your success for future chapters. So it's really important you take thorough notes, you go back and you replay anything that you do not understand. You come to me in class the next day after you listen to this with questions so that I can answer them for you. And you really make sure that you get a strong foundation in this. Because of the length of the chapter, I will be dividing this test up into two separate tests. Section 2.1 and 2.2 will be one test, and sections 2.3 and 2.4 will be another test. And I'll have to tell you, this test typically tends to be hard. You can't just memorize. You have to be able to make connections. You have to understand the concepts. You need to be able to apply and use your critical thinking skills in order to be successful. So when you're taking notes, take notes with that in mind. Okay, so our key concept for Section 2.1 is going to be what three subatomic particles make up atoms. And we're going to ask what we know about these particles. So let's first start with what subatomic particles make up of an atom. Well, first we have to understand what an atom is. And by definition, as you can see right here, the atom is the basic unit of matter. So I always ask, well, what's matter? That's a little pun there. Matter is anything that has mass and takes up space. So we're talking about something that has mass and takes up space. So you're probably sitting there and you're saying, Mrs. Saunders, air can't possibly have any mass and can't take up any space. And I would probably say to you, yeah, no, you're wrong. Because what happens when somebody walks by you? Do you feel a breeze? Do you feel air? And that's because when somebody walks by, they're displacing that air. They're moving it out of their place. And you can feel that air being moved out of its place. So that means even something you can't see has mass and takes up space. And that if it has mass, it's made up of something, and what it's made up of is an atom. So how do we know this? Well, there was a Greek philosopher who lived about 2,500 years ago, and his name was Democritus, and he was the one who discovered or talked about the atom. What he wanted to do is he wanted to see how much you could divide a substance until you no longer had that substance. And what point can you break it up and it doesn't change into something else? So he discovered that if you broke a piece of matter up to the smallest fragment, you would get an atom. And he chose the word atom from the Greek word atomos, which means unable to be cut. So just, think of taking a big chunk of cheese and then cutting it as real tiny as you can with your knife, and then getting a scalpel and then putting it under the microscope and cutting it into tinier, tinier pieces until it can't be cut anymore, and you're going to wind up getting this atom. Okay, there's a video here in section 2.1 that if you cannot play on this, we will watch in class. Okay, so you get the idea that if we can't see it and we can't cut it down any further, that atoms have to be really, really small things. And if we were to place atoms side by side, about 100 million atoms would make a row of only about 1 centimeter long. And take a look at your little finger. That's about the width of your little finger. Okay, so 100 million atoms to make that distance. Wow. So it's really small, but it's even made up of even smaller subatomic particles. And the particles that make up an atom are the proton, the neutron, and the electron. So let's take a look at the picture that we have here. Okay, see this picture? This is what an atom looks like. And in the center of this atom, this is called the nucleus. Kind of like a nucleus of the cell. And that nucleus is made up of positively charged particles called protons. That's why we have a plus sign here. And negatively charged, or I'm sorry, take that back. And neutrally charged particles called neutrons, the purple ones that you see here. So this makes up a dense center region of the inside of the atoms. The number of protons and the number of neutrons make up that nucleus. Now, surrounding that nucleus and constantly moving are negatively charged particles called electrons. So they orbit, they surround the nucleus, and they're moving constantly. Some are moving in this direction, some are moving in this direction, some kind of make a figure 8 movement, but they're constantly moving, and they're negatively charged particles. So we're looking at a molecule of carbon, and I know it's carbon because the number of protons determines the atom. It determines the atom type. So if I were to count the number of protons that I have, 1, 2, 3, 4, 5, 6, and look at a periodic table of elements for which one has 6, it's always going to come up to be carbon. Okay, there's more that we need to learn about this. So let's focus on those protons. So protons and neutrons, they have about the same mass. So mass, when we think about the Earth, mass is on Earth equivalent to weight. So gravity makes it weigh something. But if we were out in space and we didn't have any gravity, then we really don't have weight. And then that's when we have mass. The protons, as we have already identified, they are positively charged particles, and the neutrons carry no charge at all. But there are strong forces that exist between the protons and neutrons that hold them together and make that nucleus of the atom that we talked about. The electrons, these are negatively charged particles. And when we compare the size of the neutrons to the protons, and let's do it this way. This little dot is going to represent an electron. This is going to represent a proton. So electrons are really, really tiny, tiny subatomic particles within this atom, and they only have about one in 1,840 times the mass of a proton. Now electrons, as I suggested, they're in constant motion. They're constantly spinning around the nucleus. Because they have that negative charge, they are attracted to the positive proton that holds them into place. So as you can see here, we have 1, 2, 3, 4, 5, 6 protons, which means we're going to have 6 electrons. So we'll see that the number of protons will always equal the number of electrons because of that negative attraction that they have. So that is going to form the atom. Because atoms have equal numbers of electrons and protons, their positive and negative charges will balance out. And because they balance out, they are referred to being electrically neutral, because they have an equal number of protons and an equal number of electrons. So an equal number of positives and an equal number of negatives, they'll balance them out to make be electrically neutral atom. Okay, what do you think would happen if the number of protons did not equal the number of neutrons? Because sometimes this could happen. I'm sure you're all really smart and you're saying, oh, Mrs. Saunders, that's going to make an isotope. So that's the next element or a key concept that we need to take a look at. And how are all the isotopes of an element similar? And then what do you think an element is? And I'm going to ask that you look up the word isotope, and you can pause this, look it up, and do you know what isotope means? Okay, so take a minute, check that out, take a pause, and then come back and listen to the rest of the video. So let's talk about elements. Elements are a pure substance that consists entirely of one type of atom. So you can have multiple atoms that make up an element. There are over 100 different known elements. Some commonly occur on the Earth. Others have been synthetically made in the laboratory. When we write elements, we use 1 or 2 letters for their symbols. So you probably know this. You've seen that a capital C stands for carbon, a capital H stands for hydrogen, a capital O stands for oxygen, and then sometimes they have 2 letters, like sodium is going to be Na, capital N, lowercase a, and mercury is going to be capital H, lowercase g. What you're seeing here in this picture is actually mercury. It's silvery in its composition, and it's kind of a liquid in its composition. So these are the different elements. The names can come from Latin, Greek terms. They can also come from people and places where they have been produced and identified. So one of the things that we talked about was that the number of protons in the nucleus of an element determines the type of atom that is, and the number of protons refers to the atomic number. When we look at the periodic table of elements, you're going to see that we keep the elements in a box, and we're going to use the symbol in the center for its name, and up either in the corner or above it is going to be the atomic number, and that's going to tell you the number of protons that it has. And then sometimes underneath that there's going to be a number like 12.01, which tells you the atomic mass, how much that atom weighs. And sometimes, and not with carbon, but sometimes you're going to see either a positive or a negative sign that will tell you if it gives up or transfers electrons. So these are some of the symbols that you would see inside of a periodic table of elements. So the number of protons will always determine the type of atom, and that never changes. So carbon, it has 6 protons, And we know it's going to have 6 neutrons to make it electrically neutral.